Today I'll be solving the final question of the 2020 HSC Maths Extension 2 exam. So we have question 16b. We've got an integral in is equal to the integral from 0 to pi over 2 of sine of to the power of 2n plus 1 of 2 theta d theta. Okay, and we have to prove in is equal to 2n divided by 2n plus 1 times in minus 1. So this is an example of a recurrence or reduction formula for an integral. So since we have sine to the power of n, we do sine to the power of 2n plus 1, we have a product of lots of sines, so it would be a good idea possibly to use integration by parts here and try to find two things that multiply to sine 2n plus 1 2 theta. Okay, so we want to find a u and a v dash that multiply to sine 2n plus 1 2 theta, and we want v dash to have a nice integral and u dash to have a fairly okay derivative. So what I came up with is to set u as sine 2n of 2 theta and v dash as sine 2 theta. Okay, and you can see both of these multiply to give this thing. Now if I find u dash, we have power rule and chain rules. So sine 2n sine 2n minus 1 2 theta, and then using chain rule we have 2 cos of 2 theta, and integrate or antiderivative of v dash will be the negative half of cosine 2 theta. And now the integral in, so that was integral of 0 to pi over 2 sine 2n plus 1 2 theta d theta, can be written. So we have uv from pi over 2 to 0 minus 0 to pi over 2 of vu dash d theta. So uv, we have sine 2n 2 theta and minus half cos 2 theta from pi over 2 to 0 minus 0 to pi over 2 of negative half cos 2 theta, and here we have a long expression which is 2n sine 2n minus 1 2 theta times 2 cos 2 theta. Okay, and d theta here. Okay, what we can see here, if we substitute 2 theta here, we have 2 theta equals pi here, 2 theta equals pi here. And what we can see is this expression over here. So that expression will have negative half sine 2n of 2 pi times cos of 2 pi. Not 2 pi, it should just be pi. And then we have a plus half sine to the 2n of 0 cos 0. So sine of pi and sine of 0 are equal to 0, so the whole expression is equal to 0, so this whole thing is 0. Okay, so now we can just look at this part. We have 2 minus signs cancelling out. We have a half and a 2 which will cancel out. So what we'll have is the integral of 0 to pi over 2 of, we'll have a 2n out at the front, and we'll have the sine 2n minus 1 2 theta, and we'll have a cos squared 2 theta. And now since sine squared 2 theta plus cos squared 2 theta will give us 1, we have 2n of 0 to pi over 2 of sine 2n minus 1 to theta. So we can write it as 1 minus sine squared 2 theta d theta. And this we can write as, we can actually add up two integrals, so we can add up the integral of sine 2n minus 1 to theta and minus it by sine of 2n plus 1 to theta. So we'll have integral of sine 2n minus 1 to theta d theta minus the integral of sine 2n plus 1 to theta d theta. And in fact, this integral over here, this is the same as replacing n with n minus 1 over here. So this is the same as I n minus 1 minus, and this is, we've gotten I n plus 1 back again. Not I n plus 1, it should be just I n. Yeah. So I n is equal to something in terms of itself. So we have I n on both of the left hand side and right hand side. So we have, now we can bring the 2n I n over to the left hand side to get 2n plus 1 I n is equal to 2n I n minus 1. And this, we finally get I n is equal to 2n divided by 2n plus 1 I n minus 1. Okay, and this completes the first part. We got the first part of I n equals 2n over 2n plus 1 I n minus 1. Okay, so now the next part, the part II is to prove I n is equal to, so now to find what I n is equal to for all values of n. Okay, so you have to prove it's equal to 2 to the 2n n factorial squared divided by 2n plus 1 factorial. Okay, so using this fact for all values of n, so this fact is true for all values of n, so we can write I n for any value of n, I n is equal to 2n over 2n plus 1 I n minus 1. But now you can replace n with n minus 1 in this formula and write everything in terms of I n minus 2 and so on. So you actually write it like this. And we can write I n minus 2 in terms of I n minus 3. And you can keep on continuing the process. And in fact, this process continues, and it continues until you have 2n minus 2, 2n minus 4, ... times 2 divided by 2n plus 1, 2n minus 1, ... times 3 times I0. Okay. And just for completeness, I'll also put a times 1 here. So it doesn't change the answer, but we'll just add a times 1 here. So you can see this is a product of all the even numbers from 2n down to 2, and this is a product of all the odd numbers from 2n plus 1 down to 1. Now we have to also find what the value of I0 is, because we can't, there's no such thing as I negative 1, so we can't use a recurrence to find I0, so you have to find I0 separately. I0 is equal to the integral of, we have, so if you put 0 here, 2n plus 1 is now equal to 1. So we have the integral of just sine 2 theta d theta. The antiderivative is negative half cos 2 theta. And we have negative half cos pi plus half cos 0, which is negative half times negative 1 plus half times 1, which is equal to 1. So you can actually replace I0 with 1. So we'll have In is equal to 2n, 2n minus 2, 2n minus 4, ... times 2, and 2n plus 1, 2n minus 1, ... times 3 times 1. Okay, now we can see we can actually take a factor of 2 out of all these numbers. So there's n numbers at the numerator, and we can take a factor of 2 out of each of them. So we'll get, we can write it as 2 to the power of n because there's n 2's. And we'll have n times n minus 1 times n minus 2 times up to 1. And we have the same thing as before here. And all the product of all numbers from 1 to n is the same as n factorial, so we can write it as 2 to the n factorial divided by 2n plus 1, 2n minus 1 times 3 times 1. Okay. So what we can do now, so we've got an n factorial here, and we want to prove this thing. So we have an n factorial squared and the 2 to the power of 2n, so we're kind of close. We look like we're kind of close, but we might have to do one more step. And what I'll do is I'll multiply the numerator and denominator by 2 times 4 times 6 times 8 times all the even numbers up to 2n. Okay, so the reason this is good is because now the denominator is a product of all the numbers from 1 to 2n plus 1. So denominator is now 2n plus 1 factorial. And numerator, this is the same as if we take a factor of 2 out of each of these even numbers, we will have 2 to the n out at the front. And when you divide every number by 2, we just have 1 times 2 times up to n. And so denominator was 2n plus 1 factorial. And this is again another version. We have another copy of n factorial. So we have 2 to the 2n times, and we have n factorial appearing twice now. N factorial squared divided by 2n plus 1 factorial. And this is what we needed to prove in part B. So the second part has been completed. So this is the second part. Okay. So now we have this integral jn. So jn is integral from 0 to 1 of x to the n 1 minus x to the n dx. And it says use the previous part to prove this value for jn. Okay, so we can see, since we want to use the previous parts, we have to kind of relate this integral to the initial integral. So a potential idea is to use a trigonometric substitution involving sine of theta in order to convert the integral jn in terms of in. So we'll see what we can do. Okay, so next part we have jn is the integral of 0 to 1 of this. Now after some playing around, it turns out the best way to get a sine 2 theta is to use some double angle formulas, and one way to achieve the double angle formula, which is so sine of 2 theta is equal to 2 sine theta cos theta, is a double angle formula. And after some playing around, you might come across this substitution: x equals sine squared theta. And when you do x equals sine squared theta, if you have a look at the bounds first, so when x equals 1 and sine squared theta equals 1, so we can make theta equal pi over 2, and when x equals 0, sine squared theta equals 0, so you can make the bound 0 and pi over 2. And find dx, we have 2 sine theta cos theta using power rule and chain rule. And this is the same as sine 2 theta using double angle formula. So jn is pi over 2 to 0, and x, so we have x to the n is sine to the power of 2n theta, and 1 minus x is 1 minus x sine squared theta to the n dx. So 1 minus sine squared theta is the same as cos squared theta using sine squared plus cos squared is 1. So we can write it as cos squared. And now we have sine to the 2n theta cos to the 2n theta d. Oh wait, hang on, I forgot to replace the dx. Oh yeah, I'll do it here. So cos squared 2n theta. Dx is sine 2 theta. D theta. Yeah. Oh yeah, this should be a d theta here. Okay. Now we can put the sines and cosines inside the power of 2n. And now using the double angle formula again, this is half of sine 2 theta. And now we can take a factor of 2 to the 2n out. And we get sine of 2n plus 1 2 theta d theta. This is in fact the same as in. So we have 1 over 2 to the 2n of, and using the formula for in, we have 2 to the 2n n factorial squared divided by 2n plus 1 factorial. So we're cancelling out the 2 to the 2n's, and we just get n factorial squared divided by 2n plus 1 factorial. Okay, and that proves the value of Jn. Okay, the final part is using the previous results, prove this inequality to the n factorial squared is less than or equal to 2n plus 1 all factorial. Okay. So the 2 to the n factorial stuff does involve the values of the previous integrals, so we could try to find an inequality involving the previous integrals. Okay, so what I noticed was the following. We can bound sine of 2 theta between 0 and 1 when 0 theta is between 0 and pi over 2, because sine of 2 theta is between 0 and pi, so sine of 2 theta is between 0 and 1. That means when you take sine to the power of 2n plus 1, since it's between 0 and 1, it's going to shrink in size, or if it's equal to 1, it's going to stay the same. So it's going to be squished between 0 and sine of 2n. So this is for all n. And this means if we integrate the sine of 2n plus 1, since this function is always at most this for all values of theta between 0 and 2 pi over 2, it means the integral of this will be at most the integral of this. And this is equal to I0 from earlier, which is equal to 1. So this integral is always at most 1. Okay, and remember the value of in was 2 to the 2n n factorial squared over 2n plus 1 factorial. And in is always at most 1, which means 2 to the 2n n factorial squared is always at most 2n plus 1 factorial. Now we can actually have two numbers that are squared, so we can actually put it all into 1 and square it. And in fact, this completes the proof of the final part. So 2 to the n times n factorial all squared is at most 2n plus 1 factorial. Okay, so that is the final part, and this completes the final question of this HSC exam. Okay, so hope you enjoyed this video. Thanks for watching, and I'll see you next time.